Today, we're diving into the hidden physics of motion. We're going to uncover the fundamental rules that govern everything from a gentle push to a massive collision. And it all comes down to understanding one really powerful concept: linear momentum. Just look at this. In this single, frozen moment, a golf club is transferring an absolutely incredible amount of force to that ball. We're talking about contact that lasts for just a few milliseconds, but it's enough to send it soaring. So how on earth do we predict what happens in a violent, instantaneous event like this? Well, that's exactly what we're here to figure out. I know, right? They seem totally unrelated. But in the world of physics, they are all governed by the exact same, surprisingly elegant set of rules. And once you master these rules, you can predict the outcome of pretty much any interaction in the universe. So here's our game plan for today. We'll meet the main player in all this, learn the 3 rules of the game for any collision, check out some advanced plays, and then we'll put it all into practice. Let's get started. Okay, before we can even talk about the rules, we need to meet the star of the show. Seriously, to understand any collision or any explosion, you first have to get a handle on the core concept of momentum. So what is momentum, really? Well, the easiest way to think about it is as mass in motion. The formula is super simple, just mass times velocity. But here's the crucial part, the thing you have to remember. Because velocity has a direction, so does momentum. It's what we call a vector, and that means direction matters a lot. Now, what's really cool about this comparison is how it shows that both mass and velocity are key players. You've got this massive dinosaur, moving at a pretty slow speed, but its momentum is huge, 54,000. Then you have a much lighter car, but it's moving way faster, and it still has a really significant momentum. It's the combination of the two that really packs a punch. All right, now for the most important rule of the game. This is the bedrock principle of every interaction, the law of conservation of momentum. Think of this as the unbreakable rule for any event happening in a closed system, which is just a fancy way of saying a system where there are no outside forces like friction messing things up. This is it. This is the core idea. The total amount of momentum in a system that's left alone never ever changes. But why? Well, it's not magic. It's a direct result of Newton's third law. You know, for every action, there's an equal and opposite reaction. The forces inside the system, like 2 balls hitting each other, are internal. They come in these perfect pairs that cancel each other out, so the total momentum has to stay the same. Let's look at a classic example, a cannon firing. Before the explosion, the cannon and the cannonball are just sitting there, not moving. So what's their total momentum? 0, right? So according to our golden rule, what does the total momentum have to be after it fires? You guessed it, it's still got to be 0. Let's see how that's even possible. Okay, here's how the math plays out. The total momentum starts at 0. After firing, the cannonball zooms forward with a big positive momentum. To keep the total momentum of the system at 0, the cannon has to gain an equal and opposite momentum. When we solve the equation, we see the cannon's velocity is negative 0.23 meters per second. That negative sign is everything. It's the physics of recoil, telling us the cannon moves backward. And the exact same principle works here. You've got 2 ice skaters just standing still, so total momentum is 0. One pushes the other, the 65-kilogram skater moves off with a positive velocity. For the total momentum to stay 0, the heavier 80-kilogram skater absolutely must move in the opposite direction. And because he has more mass, he moves a bit slower to perfectly balance everything out. The math proves it every time. So if momentum in a closed system is always conserved, how do we ever change anything? How do you get a ball moving to begin with, or stop a moving car? Well, you need to apply an outside force, and that brings us to our third and final rule, the concept of impulse. Impulse is just the special name we give to a change in momentum, and it's equal to the force you apply multiplied by how long you apply it for. This relationship is incredibly powerful. It's literally the reason airbags work. By making the collision time longer, they drastically reduce the force your body feels, even though your total change in momentum is exactly the same. Let's apply this idea to a real-world scenario. A tennis serve is the perfect example of a huge force being applied over a very, very short period of time. This interaction creates a massive impulse, and that's what dramatically changes the ball's momentum from 0 to super fast. So we can calculate the ball's change in momentum, which turns out to be 3.3. Now, since we know this happens in just 0.025 seconds, we can use our impulse equation to find the average force. The result
is a whopping 130 newtons. To put that in perspective, that's like the force of lifting a 13-kilogram object, about 28 pounds, all focused on that tiny tennis ball. And if you thought that was intense, check out the golf swing. The contact time here is just 0.03 of a second. Following the same steps, calculate the change in momentum, then divide by the time, we find the average force is an incredible 600 newtons. This is how you get such massive forces in sports without things just instantly falling apart. So we've established our golden rule. Momentum is always conserved in a closed system. But there's another form of energy in the mix here, kinetic energy, which is just the energy of motion. And whether that energy is conserved or not adds a whole new layer to the game. Okay, let's make this simple. In any collision, momentum is always conserved. That rule is unbreakable. The real difference between these two types of collisions comes down to kinetic energy. In a perfectly elastic collision, kinetic energy is also conserved. Think of two billiard balls bouncing perfectly. But in an inelastic collision, some of that energy gets lost as heat, sound, or damage, like in a car crash. The collision of snooker balls is pretty much the poster child for a nearly perfect elastic collision. They're designed to be incredibly hard so they don't deform, which means very little energy gets wasted as heat or sound when they hit each other. Let's actually prove that with some numbers. So, was the collision elastic? To find out, we just need to compare the total kinetic energy before and after the hit. Using the formula 1/2 mv squared, we find the total energy before was 0.9 joules. After the collision, what's the total kinetic energy? Well, it's still 0.9 joules. Since the energy we started with is the same as the energy we ended with, we've just proven this is an elastic collision. All right, you've learned the rules of the game. Now it's time to put these principles into practice and see how they can solve some real-world physics problems. This is where it all comes together. Let's start with the basics. For a single object, like the car, calculating momentum is pretty straightforward. For a system with more than one object, we just have to add up the momentum of each individual piece. And as you can see, for the car, it's just mass times velocity, which gives us 18,000. For the two-object system, we do the same thing, but since that second object is just sitting there, its momentum is 0, so the total momentum of the whole system before they even touch is just 6. Okay, now for a classic inelastic collision. The key phrase to look for here is, they stick together. That's a huge clue. It tells us that after the impact, we're not dealing with two separate objects anymore. We're dealing with one single object with a new combined mass. But our golden rule, conservation of momentum, is still our guide. The logic is exactly the same for both of these problems. First, calculate the total momentum before the crash. Then, you set that equal to the final momentum, which is just the new combined mass multiplied by their final velocity. And it makes sense, right? Because that initial momentum is now being shared across way more mass, the final velocity has to be lower. Okay, let's step back from the numbers for a second and tackle the most important question of all. Why? Why does this whole conservation thing even work in the first place? What's the fundamental reason behind it? And the answer takes us right back to Newton's laws. In a closed system, there are no outside forces pushing or pulling to change the total momentum. All the forces that matter are inside the system, like the force of one skater pushing on the other. And those forces always come in equal and opposite pairs. They perfectly cancel each other out, so the total momentum of the system as a whole simply can't change. So, I'll leave you with this thought. We've seen how impulse, force multiplied by time, is the secret behind safety features like airbags. By making the time of an impact longer, you reduce the peak force. But this principle is absolutely everywhere. Think about the bubble wrap in a package, the soft mats in a gym, or even how a baseball catcher pulls their glove back as they catch a fastball. The physics is exactly the same. So, where else do you see it at play?